Okay, so now we will talk about support vector machine in detail so that you could be more powerful in machine learning, or you will be having a powerful algorithm in your toolkit of machine learning. So support vector machine is a supervised learning algorithm which is both for classification and regression. We have seen logistic regression, and logistic regression is for classification and linear regression is for regression. So support vector machine is for both, which is classification, and one more, which is regression task. Okay, so regression task. So support vector machine can be used in classification, either your output in discrete value, or it can be used in continuous value. Okay, so I will dive into the support vector machine, but before that, let me tell you what we are going to study in this section. So we'll start with the introduction of support vector machine, then we'll go further into what SVM do, and then we'll talk about linear, hard margin, then we will go further into nonlinear classification, and then we'll talk about empirical risk minimization, and then a semi-supervised constructive SVM, and then we will talk about SVR, which is support vector regression. Okay, and in the next section we will do one project, which is stock price prediction project. Okay, so what is SVM? What actually SVM does? It's simply just what is like this. So let me draw one X and Y plane. So here is my X and Y plane. I hope that's beautiful. So here is my X and Y plane, and let me make a linear data. Okay, so here we have the one data point, and another data point is over here. Okay, so we have like this, and then we have this data. Okay, so let's assume that you are working on CAT and a non-CAT recognition system. Okay, so you are working on CAT and non-CAT recognition system. So what actually SVM does is, here you can see over, let's assume that white color is for CAT images, means the labels are CAT, and blue color let's take as a non-CAT. Okay, so these are data, and what SVM does, it construct a hyperplane. It's construct a hyperplane like this. It's construct a hyperplane like this. Okay, and now whatever new point come on or beyond here, then this example will be CAT. Otherwise, if something come here, then it will be non-CAT. Okay, so this is what SVM does. But this is not the full procedure. I will tell you. But here what it does, it simply construct a hyperplane and two parallel hyperplane, and two parallel hyperplane with this margin. Okay, these are called a margin, so it always tries to maximize that margin. So it may sound a little bit kind of confusing, so let's draw it again to let me show you once more time what actually it does. Okay, so here is your white examples, and here is your blue examples. Is it non-CAT and not CAT? So what it does is construct a hyperplane and a two parallel hyperplane over here, two parallel hyperplane like this. Okay, so, and this is called the margin, and SVM always tries to maximize this margin, keeping away the nearest data point far away from the hyperplane. What I've said is very crucial to listen what I'm saying. I'm saying that what SVM does, it simply constructs a hyperplane and a two parallel hyperplane that separates the data point and at a maximum margin. Okay, so SVM always wants to maximize that margin in such a way, so that the nearest data point, let's say xi, is far away from the hyperplane, this hyperplane. Okay, is far away from the hyperplane, so that it will be easily, so that whatever comes here, then it will classify as a non-CAT. Whatever comes here or here, it will be classified as a CAT. Okay, what I'm saying that the nearest data point, and the nearest data point is should be the far away from the hyperplane here. Okay, so it would be here. So these are called the support vectors, who are the nearest data point from the hyperplane. Okay, and that is supported by these are the support vectors which supports this parallel hyperplane to separate this. Okay, again it may sound a little bit confusing, so let's revisit this again in a more detailed way. So let's say let's take another example, that we are building a person has a cancer or a non-cancer, I think malignant, let's say a non-cancer. Okay, so you build x and y plane. So let's build one x and y plane, and then you put this blue examples which indicates as a cancer, and this white example which indicates as a non-cancer. Okay, so what SVM does, simply construct a hyperplane like this. Oops. It simply constructs a hyperplane and a two hyperplane like this, and a two hyperplane, and this is called the margin, and it always tries to maximize this margin, so that in such a way that the nearest data point is far away from the main hyperplane. Okay, so you can see over here that this is the nearest data point is far away, so these are called the support vectors. Okay, pretty much easy. Now I think that is much clear. We have taken 3 examples. Now I think this is much clear. Okay, so it may sound to you like it's like a linear regression. You have a linear data and you're just fitting a straight line with 2 hyperplanes. What does it mean? Yeah, it obviously means like linear regression. But if you come to the more in detail, the data are not linear. Okay, the data are never linear. So there are 2 kinds of SVM there. The first kind of is hard margin classification and soft margin classification. Okay, so let's visit hard margin first, and then we'll revisit soft margin. Okay, so here you can see over here that this is just like linear regression, but wait for a few seconds, few minutes, then you will understand why it is not like linear regression. Although it seems like that you have simply constructed a straight line, but equation and is used for classification is quite different. Okay, so it's called the linear SVM. The what we have seen is called the linear SVM, where we are constructing a simple hyperplane and separating 2 data points. Okay, so what are hard margin? Hard margin means that we are not allowing any data point to come into that margin. Okay, that's called the violating the hard margin. So sorry, violating the margin. So we are not allowing any data point to violate that margin. So in that way we end up being an overfitting, or in that way we very much our model is being started overfitted. So let's see what I'm trying to say over here. So let's construct a let's construct one x and y plane again. So let me construct one x and y plane. Oops. Here is my x and y plane, and let's draw 2 data point. Again, let me draw 2 data point like this. Okay, and let's draw a white data point like this. Okay, so and now what SVM does, simply construct a straight line with 2 hyperplanes. Okay, with this hyperplane. Okay, so in hard margin we are not allowing any data point that you can see over it comes under in, so we simply kind of do like this. We simply minimize this margin like this. So we are doing like this. It is very strict. Hard margin is very strict. The reason I'm saying is very strict because it just does not allow any data point to come into that margin. But in soft margin, we allow some data points to violate that margin to avoid overfitting. Okay, so that's what the soft margin and hard margin means. Hard margin means we are not allowing any data point to come into that margin, and soft margin means we are allowing a little bit of data point to come into that between. And the width is the width of the margin. This is the width of the margin. is adjusted by C. Okay, so if C is very large, then your width will be very small, like this. Okay, it's, let's say C equals to 0. This is the margin, my margin. So this is my margin. So let's say your C 100, C equals to 100. So your margin will be very the width of the margin is kind of a low, means it's very slow, kind of it's very small. But if C equals to 1, then the width of the margin will be very large. Okay, like this. So it's kind of a very awkward thing that you can see over here, but that's what the convention said. Okay, so we have seen this kind of thing, and maybe you will see sometimes C to be named as lambda. Okay, it's just the same, lambda and C are the same. Just as convention, we give it a C as a name. Okay, so let's just get now you got the overview of this hard margin and SVM. So we have seen a lot more things. Now it's time for getting into the little bit of mathematics, which is how do we construct that hyperplane. In linear regression, we are just making the straight line and this theta transpose x. But this was our favorite equations, like this, theta 0 times x 0, and in logistic regression we are just doing the sigmoid of z. So these are our hypotheses. So from this equation we were making our straight line, or maybe the sigmoid. So what happens in case of a supported machine? Our hyperplane is defined by W transpose x minus b equals to 0. This is the condition that our hyperplane should satisfy. Okay. So what is this? This W is our parameter weight. In linear regression we have seen is theta, and b is our biased term, which is in case of linear and logistic, which is theta 0. Okay, so we have just given a new name, which is W and B. Okay, and so we have made a W transpose x minus B, and this is our hyperplane that we have made as W and B are the parameter weights. Okay, so we have just given a new name, and transpose, you all know in linear algebra, and this is W is a parameter vector. Okay, so let's define some constraints for hard margin. So let's define some constraints for hard margin, how hard margin make predictions. Okay, so whatever the output of your model minus W transpose x minus b is greater than or equals to 1, then anything on or above this margin will be regarded as 1. In this case it will be cat. Okay, why I'm saying like this is, let's say you have this straight line and you have this, and you have the data point and these two parallel lines, and again here you have. So whatever on this margin or above this margin is regarded as 1, means the positive attention, so it is regarded as a cat, as you know. Okay, and whatever below this is regarded as a 0. Okay, as a non-cat. Okay, so let's write the equation for that, and it's quite easy. It's quite rememberable. Like W transpose x minus b, whatever on or beyond this margin will be regarded as 1. Whatever below this margin will be regarded as a 0. Okay, as a negative attention. So that is the hard margin constraints, and that's how we make predictions onto support vector machine. Okay, pretty much clear what I'm trying to say over here. Okay, so now let's dive into little bit more further into math, is how actually it is being constructed like this. So let's say you had made a straight line, and this margin, you can see over here, this margin is written by this hyperplane. The main hyperplane is written by W transpose x minus b, and this margin is equals to 2 over the norm of W. So to maximize this margin, we wanted to minimize this margin, minimize to W. Okay, if we want to maximize this margin, because SVM always has to maximize this margin. To maximize this margin, we have to minimize this norm of W, and this margin is written by 2 over the norm of W. Okay, and so as you have said, the SVM always tries to maximize, so that is written by the 2 over norm of W, and to maximize that we want to minimize the norm of W. So we can write an objective function, we can write an objective problem like this. The distance between two hyperplane, the distance between two hyperplane is written by 2 over the norm of W. So to maximize that margin, we want to minimize the norm of W with subject to yi double transpose xi minus b greater than or equals to 1. So what I have said, so let's understand this equation little bit more further, what I have written over here. So for maximum, this is the minimizing, means we want to minimize to maximize that margin with respect to yi, which is your ground truth, means actual label, and this is your moral predicted value, and you can show here if it is on or beyond this, it will be 1, otherwise it will be 0. So if yi is equals to your moral predicted value, then your cost function will be 0, then your loss function will be 0. Otherwise, if it is not equals to y, then your loss function will be very, very high. So you want to minimize this norm of W to get the good predictions. Okay, so we have started this, and I really hope that you had understood the concept that I explained to you, and we can write our cost function in a hinge loss. For I'm talking about some soft margin, so we can write our soft margin like this. So we can write the loss function, the cost function, the loss function. We can write our loss function like this: 1 over n plus, I'm going to each and every training examples, max of 0, 1 minus y double transpose xi minus b plus regularization plus lambda over times the norm of W squared. Okay, so this is quite confusing a little bit, but let me try to explain you in more detailed way. So you can see we are going to each and every training example, but take note of max, and this is the hinge loss. If you can see, this is called the hinge loss. If you want to get into more detail about a hinge loss, you can have a look at some Wikipedia pages for knowing about hinge loss. Okay, and this is your model predicted value yi, and ground. This is your ground truth yi, and this is your model predicted value, and this is the lambda times. You can write it c also. You can write c also because it help you to adjust the width of that margin. So that's why it is a very, very important hyperparameter. Okay, and times the norm of W squared. Okay. Okay, so we are done with a kind of a linear classifier. We are linear SVM, is linear classification. So we have made our good loss function. So we have made a prediction function, and now it's okay. We want to minimize this norm of W to get the good predictions. Okay. Okay. So we have seen only the linear SVM. So let me formulate one example, which is like this. Let me make one again x and y plane. I'm making too much x and y plane. It's best to have this kind of things. Okay. So let me make one non-linear classification like this. Okay. So you have this kind of data and this kind of data, and let me make these white examples are cat images, and these white examples are non-cat images. So now if you want to make the straight line, you will be not able to do that. Means you're not able to kind of classify it. So it's very bad. So what you have to do, you have to make a non-linear. You have to do the non-linear classification like this. Now it will be okay. Now it will be okay. So SVM also is very kind of powerful in non-linear classification with something called as kernel trick. It's something called as kernel trick. So we will elaborate kernel trick in detail. So let's start with kernel trick. So what we do in kernel trick? So let me write an algorithm. So what you do, you write an algorithm in terms of x. You write the inner product. Let me write. You write an algorithm in terms of the inner product of x and z, and these x and z are two data points. So what you do, let me tell you what we do in nonlinear classification. We take our data x, and we transform our data to some more, let's say we have one-dimensional data to a two-dimensional data in nonlinear classification. Okay, so we transform our data from one-dimensional to two-dimensional, like this. So okay, so we write an algorithm in the form of x and z are the data points. So simply in Kernel Trick, we transform our data from one-dimensional to higher dimensional space. So you will get to know what we are doing. So let me write the steps. So after we have written our algorithm in terms of the inner product of x and z, now what we do, we map our input this x. We map our input x to the phi of x. Okay, to the phi of x. So we are just, I will tell you what this function is. Okay, so we write our function. We map our x to the phi of x. I will tell you what we do in this case. So we find a way to map our this. We find a function. So we map our x to the phi of x. So we write a function, or we find a way. So we find the x to the some phi of x, and it will transform your one-dimensional data to the maybe any kind of your data to be the high dimensional. Okay. So you write a function at k which transform a data the phi of x transpose the times the phi of z. Okay, so let's see what it does with the help of an example, and then what we do, we replace our x and z with our transformed data, which is phi of x, and z to be the phi of z. Okay, so this is what we do. So let's see what it does and what way it does. So we write the kernel functions are one of the famous kernel is RBF kernel that will transform your data x and z to the high dimensional space. So the kernel function is written by the RBF kernel function written by k of x comma z exponent of minus norm of x minus z squared over 2 over the sigma squared. Okay, and the x and z are the data points. Okay, great. And some more kernels are, which is polynomial, homogeneous, polynomial, inhomogeneous, which you can search on internet, but the most famous one is RBF kernel, which is widely used in the industry. Okay, so we have seen various kind of things and about kernel trick, how we do the nonlinear, the transform data, you're able to do the nonlinear classification. So here are we will discuss one primal problem which will help us to state our optimization objective, and then we will see the subgradient. Okay. So why I'm talking about primal problem, it will help you to formalize your objective function. So it will help you to formalize your objective function. So it's just the same, just as written, we write that. So for each I be the member of 1, 2, all the way down to the n, we introduce a new variable zeta. Where zeta I where is equals to the max of 0, 1 minus yi. So we introduce a new variable zeta I 0, 1 minus yi. Okay, and then in that we write w transpose x minus b. Okay, so this is just a hinge loss where we introduce a new variable that hinge loss is storing. Okay, try to see what I'm trying to say you here. Okay, so then we write our function like this. You want to minimize 1 over n, I equals to 1 all the way down to the n, zeta I plus the regularization term c, the norm of w squared. Okay, with respect to or subject to yi w transpose x minus b greater than or equal to 1 minus the zeta I is just where zeta I is greater than or equals to b for all I. Okay, so we have just formulated one problem. It is just equal to the hinge clause that we have seen. We want to minimize the objective function that we have seen so far. It's just equal to that. So we have formulated in such a way that we can use this. Okay, so we have an objective function, which is our cost function. Now we can something called as subgradient, descent, and what we do, we make a convex function f of w and b. We take out the subgradient of our function. We take out the subgradient of our cost function, and then we update our parameter w and b. Okay, and that's the as a gradient descent what we were doing. Okay, so it's little bit different than gradient descent. Here we are taking the subgradient of our cost function. Okay, so this is what we are doing. This is called the primal problem, and then we take out the subgradient of that primal problem. Okay, pretty much easy what I'm trying to say here. Okay, so one more thing that is very popular among beginners or learning theory, something called as empirical risk minimization. What do you mean by empirical risk minimization? Given the input x1, x2, all the way down to the xn, you want to and given y1 all the way down to the yn, you want your output yn plus 1, given xn plus 1. So it's just the same. You give a function x and you want your output y. Okay, and the loss and the getting the error should be minimized. Means the risk should be minimized. So that's the empirical risk minimization, which we have already seen. So we just have to know the definition for it. What is S? Okay. So as we have talked about nonlinear and linear, now it's time for getting into the support vector regression. I'm just going to give you the equations. Okay, it is kind of quite easy. You want to minimize your 1/2, the norm of w squared. You want to minimize this to get your output with respect to or subject to the yi, the absolute value of yi, minus the inner product of w and xi times b, and it should be greater than or equals to the sum epsilon, and epsilon be the smallest positive integer. Okay, so just to be comfortable into that, so I hope that is quite clear, and this is for regression task. Okay, and we will see the implementation in our next section. So I hope that you really enjoy this tutorial, this section, and we will be carrying out this more into detail. Now, if we have gone too much into math, but if you haven't understood anyone, please feel free to put your comment in the comment box. I'll be very happy to take your comment and provide you answers over there. I will be taking a look at your questions, and we'll be answering soon at that point. So just put the timestamp where you're commenting, okay, so that I could know where you have a problem. Okay, so I think that we have gone in too much detail. If you haven't understood primal problem, subgradient, don't worry. It is not required for a beginner machine learning. So if you learn too much in machine learning and gone into deep learning, now you can come back to this primal problem to understand what I'm saying. But it's quite easy to understand, and the kernel trick, what I've said, etc. Okay, so thank you for seeing this video. Thank you for seeing this section. I'll be catching up you in the next section. Till then, you can do the programming assignment. Okay, I'll be catching up your next section. We'll be making one project which is stock price predictor. Okay, thank you.